Pleasant day to everyone. Today we're going to discuss part 2 of Module 3 for the subject CE4111, Highways and Railroad Engineering. So in this lecture, we're going to discuss the application of sight distances to the vertical alignments of roads. So the sight distance for vertical curves would be the distance along the roadway throughout which an object of a specified height is continuously visible to the driver. So this distance would be dependent on the height of the driver's eye above the road surface, the specified object height above the road or your obstruction, the height of the obstruction, and the height and lateral position of the obstruction within the driver's line of sight. So similarly, for horizontal curves and vertical curves, the stopping sight distance is an important factor for our design. So for crest vertical curves, its summit or the highest point would usually obscure objects on the other side of the curve from the vehicles coming up on the road. So if we have here an upcoming vehicle while it's moving towards the summit, then dito siya, hindi niya makikita yung obstruction natin na nandun sa kabilang side because of the summit. So you have to design what is a safe stopping distance or passing distance between the approaching vehicle and an obstruction along the opposite side of the road. And then, for sag vertical curves, there would be the issue of undercrossings. So for example, we have a curve, sag curve here. So ito yung undercrossing ninyo. Meron siyang structure above. So this is usually is what you expect when we have sag vertical curves. So kung wala man itong structure dito sa taas, there's no undercrossing, then there's still a design when it comes to sag curves. And usually this is more applicable during nighttime, since during daytime on sag curves, drivers would be able to see our obstructions on the opposite side, since wala naman nag-obscure doon sa kanyang line of sight, unlike for crest vertical curves. So during nighttime, doon nagkakaroon ng problema. So for sag curves, the headlight sight distance would be your controlling factor in your design. Though in actual design, what is used would be the stopping sight distance. But our computation for that would be dependent now on the headlight height of your vehicles. Okay. So the standard heights for our design for vertical curves would be as follows. So this is taken from the book of Sigwa. So for the stopping sight distance, we have for each one, which is the driver's eyesight, and each two, which is the height of the object or the hazard that is seen along the path. So each one now is equal to 1.14 or 3.75 feet. And this is the same value that you can find in your modules. And then for each two, that is now equal to 15.24 centimeters or 6 inches. Okay. And then for the passing sight distance, your each one now is equal to 1.14 meters, or same the height of the driver's eyesight. And then for each two, that is now equal to 1.37 meters or 4.5 feet. So we assume that the height of the other vehicle is larger than the approaching vehicle. So an application of your sight distance would be on mining tracks. Okay? So this is taken from the 2018 Journal of MPES. So an unsafe sight distance would usually be less than the stopping distance. So this is your required so that you'll be able to react on time when you see the hazard. Pero yung sight distance lang na meron tayo is at this point. Okay? So the vertical curve is lesser compared to a safe sight distance wherein we have a larger curve or radius is enlarged now to obtain a safe stopping distance. So with this greater curve or radius of a curve, then at this point you'll be able to see now the hazard on this way. Okay? So for crest vertical curve, we have the stopping sight distance. So the stopping sight distance S now, comparing to L, we have two cases. So the first one is when the value of the sight distance is lesser compared to the length of the curve. We now compute for L as equal to A times S squared divided by 100 times the square root of 2h1 plus the square root of 2h2 quantity squared. Or this could also be another case wherein S is greater than L. So L now is equal to 2S minus 200 times the square root of h1 plus square root of h2 quantity squared divided by A. Okay? So another equation for the length of the curve, aside from our parabolic equation, is the product of your k value and A, wherein k is simply a measure of curvature of the vertical curve, which is in terms of meters. And as we have already introduced, A is simply the absolute difference between the grades G1 and G2. So for the value of A in our equations, for S less than L and S greater than L, take note that A here is, or this equation is only applicable if the computation of A is in percent. Okay? So kung yung percent value ang ginamit natin, we use this equation. But if we have computed for A in its equivalent, or computed A with the grades in its equivalent decimal form, ibig sabihin we have multiplied our grades by 100 and then have taken its difference, then this equation now will slightly change. So what will happen is that so pag ang E natin is in, if the G's used for the computation of A is not in percent, then our equation will simply be AS squared divided by the quantity square root of 2h1 plus the square root of 2h2 squared. Okay? And then for this equation, if the computation of A now use the value of G times 100, then our equation will become 2S minus, so 200 becomes 2. Okay? So times the quantity square root of h1 plus the square root of h2 squared all over A. Okay? So parang dinivide lang natin. So yun lang yung difference. So pag yung E natin is naka-percent, then we have to, the factors will be in its hundreds. Pag minultiply natin yung G1, G2 in 100, then divided by 100 lang yung constants nyo dito. Okay? So for our H1, H2, we are given in the previous slide, H1 is 1.14 meters or 3.75 feet. or we have 1.08 meters or 3.5 feet. Then for trucks, the height distance or the driver's eyesight now when he is in a truck would be ranging from 1.8 to 2.4 meters, and the recommended value would be at 2.33. So if there are no given values in the problem, we automatically use for each one. For passenger cars is 1.08 meters or 3.5 meters. And then for trucks, we automatically use 2.3 meters. And then for H2, we were given in the previous slide that H2 is 15.24 centimeters or 6 inches. Or we have 0.6 meters or 2 feet. So again, if there is no H2 given in the problem, automatic value will be this value. Okay, so why this value? Remember that each one, H2 is or are the values from the book of Sigwa and from your modules, which were taken 1980s pa. So these values now are values taken from the 2011 edition of the AASHTO, which is our standard for highway and railroad design. So these values now, the 1.08 meters and the 0.6 meters are taken from a study by the AASHTO, wherein for each one, the driver's eyesight for passenger cars have been reduced from a 1.14 to 1.08. Kasi before, there were higher height of vehicles. And from that study, there was a decrease of height to 1.3 meters. So the vehicles at these days have heights of 1.30 meters na lang. Okay? And with this decrease of height in cars, there was also a comparable decrease in the average eyesight or height of eyesight by the drivers. That's why from 1.14, it became or it was decreased or reduced to 1.08 meters. Okay? And then, likewise, from that same study, the object height now, which is from 6 inches, it became 2.6 meters because from that research, it indicates that objects having heights less than 0.6 meters were seldom involved in accidents or road crashes. Meaning, this height na 6 inches, if you compare 15.24 centimeters would be like 1/4 of this value. So, lesser than this value, hindi siya masyadong prone sa accident. Yung talaga nakakapag-cause ng accident would be those at H2 equal to 0.6. That's why, from that study, they have concluded that the representative value of the smallest object that would involve or introduce risk to drivers would be 0.6 meters. So again, if there are no given values in the problem, then automatic value of each one will be 1.08 meters for passenger cars. And then for trucks, automatic value for each one, if there are no given values, 2.33. And for each two, that is 0.6 meters. Pero pag may value na given sa problem, you use the value given. Okay? So, aside from that, heights of less than 0.6 meters for our sight or stopping sight distance calculations would usually result in longer crest vertical curves without a documented decrease in the frequency or severity of the crashes. So in that case, if you're going to use smaller values of H2, values smaller than 0.6, this would now cause us a substantial increase in our construction cost. So since we want to have an economical design, then we have to follow now H2 equal to 0.6 meters. Okay. So for the next sight distance for vertical curves, we have your passing sight distance. Okay, so it will also be dependent on our S, the length of the curve, G1 and G2, as well as the heights of your approaching vehicle and the vehicle that has to be passed. So for the crest vertical curves, our approach would be likely the same as for stopping sight distance. The only difference is that we'll have H2, which is equal now to 1.08 as well. So we have the same height for H1 and H2. Given that, applying the value of H1 and H2 in the equation of the stopping sight distance, we now arrive at L is equal to A times the passing sight distance squared divided by 864. And this is used when the sight distance is assumed lesser compared to the length of the vertical curve. And then when we have S being greater than the length, then the length now is computed as two S minus 864 divided by 8. Okay, so again, for passing sight distance, our general equation would be the same as our equation for the stopping sight distance. The only difference is that for H2, it will now be equivalent to the height of the car to be passed, which is 1.08 meters. Okay? So kung ang i-overtaken natin sa passing sight distance now for a crest vertical curve is a truck, then H2 now will be 2.33 meters. So this one will change. Okay? So this value again is only applicable if we have a passenger car that is being overtaken, wherein H2 and H1 is equal to 1.08 meters. So unless there are other given values for H1 and H2 in the problem, then we use the equation for SSD and you use the value of H1 and H2 in the equation or in the formula. Okay? So for stopping sight distance for subvertical curves, we'll have the same approach for this. We'll also have two cases. We have when the sight distance is less than L and the sight distance is greater than L. So in here, for the first case, S being lesser than L, we'll have the equation A times S squared divided by 2 times the quantity H plus S tangent of beta. And take note that for H, that will now be equivalent to 0.6 meters or 2 feet, which is the height of the headlights. So this is the average height of headlights of vehicles. And beta will be equal now to 1 degree, which is the upward angle of your headlight beam or average headlight. So again, if there are no given values in the problem, automatic value of H for subvertical curves will be 0.6 meters, and beta will equivalent to 1%. Okay, so as I have said, for sag vertical curves, our equation now will be based on your headlight distance, because the sight distance would be restricted when it is at night or during dark. Then for headlight beams, they will now be focusing on the sight distance of our, or the sight distance now during night will be limited because of our headlights. Okay? So usually, pag daytime, yung sa sag curve, again, yung sight distance natin, kitang-kita ng ating driver. But during night, or when it is dark, the sight distance would be limited. So therefore, the controlling factor will be the distance that can be seen by the driver due to its headlight beams. Okay? So for the divergence of beam, normally, again, it's 1 degree, but it could vary depending on the problem given. Okay? So this is for our equation. So this is the general equation. If you're going to use now your constant H and constant beta, you can simplify this one. Okay. Then for the second case, when S is greater than L, then our equation will most likely be similar to our equation in the crest vertical curve. The only difference is that instead of using H1 and H2, we'll be using H and beta. So for the second case, L now is computed as 2S minus 2 times H plus S tangent beta divided by T. So take note, yung aking equation dito, the constant is 2. The constant being multiplied to H plus S tangent beta is not in hundreds, so therefore, the A value here is not in the percentage form. Okay? So take note lang natin. Yung value ng A will be, or the value of the constant will be dependent on the value of your A. To understand the applications of sight distances to our vertical curves, let us solve some examples. So we have example 1. Given the following characteristics of highway, determine the length of the vertical curve. So we have the design speed at 80 kph, your initial and final grades at positive 2% and negative 2%. We have the stopping sight distance at 110 meters and the passing sight distance at 550 meters. So for our given, we have a positive to negative grade. Therefore, this is a crest vertical curve. So walang given na H1, so automatic H1 is equal to 1.08 meters from ang AASHTO 2011. H2 is equal to 0.6 meters. So for A, this is simply the absolute value, the difference between G1 and G2. So we'll arrive at 0.04. Okay. So kahit nagbaliktad, G1, G2, okay lang as long because we'll have the same value pa rin since we are using the absolute value. Okay? So for our solution, it's a crest vertical curve. So we start off first with your stopping sight distance. So let's assume that S is lesser compared to the length. So using now our general equation, L equal to AS squared divided by the square root of 2H1 plus the square root of 2H2 squared. So as you can see, doon sa given equation natin in the previous slide, it's divided by 100 since A is in percent. But our computed A is in its equivalent decimal value, kaya wala yung 100 dito. Okay? So with that, let us substitute the value of A, S, and H1, H2 in the equation. So L now will give us equal to 73.55 meters. So comparing this to our stopping site distance, it is lesser than the given SSD. So therefore, our assumption is wrong. So dapat S must be lesser, or S should be greater than L. Okay? So with that, we now use the other equation, L equal to 2S minus 200 times square root of H1 plus square root of H2 quantities squared divided by E. So substituting our values again for S, H1, H2, and E, we now arrive at L equal to 55.5 meters. So comparing this to our SSD, it is really lesser than our SSD 110. Okay? So the assumption now is correct. Therefore, if we are considering the site distance, the length of the curve should be at 55.5 meters. Okay? So take note that for dito sa denominator natin and the numerator for this term of our equation, pareho lang siya. So ibig sabihin, itong equation na to, itong part ng equation at itong part ng equation will be the same. Okay? So ito din, compare nyo. 200 yung ginamit ko dito, yung A ko is in percent. Okay? So 4 tapos 200. Dito, 0.04, kaya wala yung 100. Okay? So this one is our solution for the given example. If you are going to use the values of H1, H2 from AASH to 2011. So from the book of Sigwa, if you have a copy, using the old values during the 1980s, the value of SSD computed will be 114 meters, which is greater than your S. So ibig sabihin, the older values using a smaller value of H2, as we have said, would be expensive. So using now AASH to 2011, our design would be more economic. Since maliit na lang yung ating L, so magkakaroon tayo ng lesser excavation for our highway. And like for this, with greater length, there will be more expenses in your construction. Okay? So for the next part of our solution, we now determine the length of the vertical curve if we are going to consider the passing site distance. So for our analysis, it's the same. We assume first a case. So in here, we assume that S is greater than L. So we use H2 equal to 1.08 from AASH to 2011 in our general equation. So with that, simplified version now of the equation is L equal to 2S minus 864 all over 8. So 864 came from our general equation using H1 and H2 equal to 1.084. So we have now L equal to 884 meters. Comparing it, L is greater than the site distance. So therefore, we have a wrong assumption. So we move to the next condition, S lesser than L. So we'll have our simplified equation now, L is equal to AS squared divided by 864. So substituting A and S, we now have 1,446 meters. which is greater than S, so we have a correct assumption. So meaning, if the PSD is to be satisfied, then the length must be 1,400.46 meters. Okay? But if it's the SST to be satisfied, then the length should be at 55 meters. Okay? But take note, comparing now our length computed, 1,400.46, as you can see, it is 25 times greater than our SSD, which is impossible to provide in actual design. So for a good design, it is usually given at 1/3 or at least 1/3 of the time or 1/3 of the value of the length. Okay, so again, comparing this to the values of sigma using the old values of H1 and H2, the computed PSD is equal to 1205.179 meters. Okay, let's have another example, number 2. Design a crest vertical curve that will connect a highway segment with a 3% grade to an adjoining segment of negative 1% grade. So assume a minimum stopping sight distance for the highway equal to 540 feet if the elevation of the vertical point of curvature is 1,500 feet. What will be the elevation of our curve midway? For our given, we're given the sight distance, stopping sight distance, 540 feet, and we have an E, which is -1 to minus -3, absolute value, so we get 4. We use now each one is 3.5 feet and each two is equal to 0.5 feet. So again, these values came from AASHTO 2011. So for our solution, so assume first S is greater than L. So using now our general equation, 2S minus 200 divided by A times the quantity square root of H1 plus square root of H2 squared. Substituting S, H1, H2, and A, we now get a value of 747.71. So comparing this to our L, it now shows an invalid or long assumption. Okay, so L should be greater than S. So we use the other equation. L is equal to A squared divided by 100 times the square root of 2H1 plus 2H2 squared. So substituting the values of ES, H1, H2, we arrive at L equal to 877.55 feet, which is greater than S. So meaning we now have computed the correct value of L. Okay, so what we want to find is the elevation of this point wherein L is over 2. So we want to find the value of Y. Okay, so for our solved value of L, that's 877.55 meters. At X, we're in L over 2. What is now the value of Y? And for the value of Y, we now apply our parabolic equation, y equal to ax squared plus bx plus c. So we know already x at 430.775 feet. So for A, that's G2 minus G1 divided by 200L, our constant. B is equal to G1 and C is equal to the elevation of the beginning of the curve. So for A, that is now equal to 4 negative divided by 200 divided by 877.55. B is equal to 0.03 and C is equal to 1,500. So substituting this in our equation, we now have 1508.77 watt. Okay? So, ito na yung final answer na, which is the elevation of the point midway of the curve or at L over. Okay, that's it for the sight distances for vertical curves. Thank you for listening. So again, for your references, we have the following books and sites.